Good afternoon, everyone. I'm introducing today's presenter, which feels a bit funny because to me she's not really new. I realized this about 10 years ago. I first met Corey, and to most of the people at this table here, Dr. Matches is pretty well known. And to the rest of you, it might vary. Some of you know her pretty well, and some don't. Some might know her just as she's the hurricane person, the hurricane guru, the hurricane rock star, and we'll say hurricane Tom McCarthy. So she's not just a great researcher focusing on hurricanes, she does a lot of other cool stuff. Amazing teacher. So if you get a chance to take one of her classes, even if you're not into hurricanes, she does other kind of hurricane stuff too. Take one of her classes. I'm one of her former students. I know she was teacher, and she's won a number of awards too. But here's your recommend that. However, today she's not going to teach us about her research, right? Which of course will be about tropical storms, but focusing on radar. So please take it away.
Thank you. A little bit of teaching perhaps to try to tell you a little bit about radar, because I know most of you don't know a whole lot about it. But before we get into that, I want to acknowledge the National Science Foundation that's funding this research, funding Zainab's dissertation work, and my collaborators, Dr. Wood at Mississippi State. She is our satellite expert, and Dr. Zick at Virginia Tech. She's working more with forecasting data, and we're using spatial metrics to look at the rainfall forecast from the Hurricane Research Division of the National Hurricane Center's models, and we've got our first paper submitted on that. So we're excited to have our first grant paper submitted. And so what I'll be telling you about today is the work that we're doing comparing space-based and ground-based radars. And so just a quick outline there. So I'm going to go a little bit longer than I normally would on some background, given that this is a very widely studied audience of different topics in geography. We're not at a meteorology conference where I can kind of, go it after the fast. And then just very briefly, there's been a couple of studies that have looked at this problem, but not for tropical cyclones. And then into the nitty gritty of the data and the methodology. And then we're doing a point-based approach and an object-based approach for analysis. So I'll talk a little bit about that before we reach some conclusions. Okay, so you might be familiar with ground-based radars. You might have an app on your phone that gives you the radar. What we're talking about is a signal that goes out, and then we measure how much comes back in a very basic sense. Now, the signal goes out, and the dish spins around 360 degrees, and then they tilt it up a little bit, spins around, tilted up, spins around, tilts up, spins around. And so you've got all of these beams that are going out and detecting different parts of the atmosphere. And so the data are considered usable out to about 230 kilometers away from each radar site. So the reason why there is a limitation here is because the beam spread. So if you think about if you have a flashlight, right, and you point it and you're close to something, it makes a small circle. But if you stand back, the circle gets a lot bigger. So that's beam spread. And so as you think about this beam traveling out from the radars, get bigger, bigger, and bigger, and bigger. The problem is the same amount of energy is detecting a large space. So now we're not getting as reliable information back. And so there is sort of a usable limit. So we'll call that 230 kilometers. So it's spreading both in the horizontal and the vertical direction. And then we also have some issues with atmospheric density that can actually bend the beam. And so it can kind of bend it up, it can bend it down. And so in reality, we don't exactly know where we are sensing. So we have sort of a standard equation that we apply for standard atmospheric conditions. There's a whole other thing, I mean, there's whole classes on this, right? But there are other things that can interfere with the signal. And so, yeah, there's a lot of work that needs to be done in terms of making sure you're getting reliable data back from the radar. So what we try to just very generally break our data sets down, right? What's the spatial resolution? What's the temporal resolution? And what I'm getting at is it's tricky for radar. So these are all the different tilts, and there's different patterns. I just have these two here because these are the two most common for the hurricanes that we sampled. So VCP is 212 and 215. The only difference here is there's just an extra couple of scans at the higher level. And so the lowest 4 scans have what's called super resolution now since about 2008. And so you get a data point back every 250 meters out, and then every half a degree around the 360-degree circle. And then in the higher elevation scans, it goes to about a 1 degree width. And so it's a little bit less resolution in those higher scans. But remember, when we're thinking about the formation of clouds and precipitation, the rain's in the bottom of the cloud. You really want to get those lowest levels scanned. Now, if you've got a lot of severe weather where you got a nice tall cumulonimbus thunderstorm, you're going to want some of these upper levels as well. So that's why they tilted up and up and up. We try to use these radars for rainfall climatologies as well as tracking severe weather events. So that's why we have multiple scan strategies that take multiple times. So it is up to the individual radar operator which scan strategy to employ. It gets complex. So if you want to try to break it down into a vertical and horizontal resolution, that it will depend on the VCP that is selected. And then to complicate things, the tilts can be out of order. So there's a new technology where you can scan, go up, scan, go up. They're like, oh shoot, we need the lowest level because there might be a tornado forming. They can tilt it back down, do that lowest level, and then go back up and go where they left off. So they're not all in temporal order now either. So that makes it really complex. So this picture here, you can kind of get a sense of like right where the beam is narrower, you're going to get better detail. So all else fails, you'd want to take the data from the closest radar to your cloud that you're trying to detect. But sometimes there's issues with that radar. They can run hot or cold, meaning the signal that goes out might be a little bit higher relative to the neighboring radars or lower relative to the neighboring radars. There is a correction that they employ regularly, but you never know where they are in that calibration, when the storms come in. And so there can be reasons why the closest radar may not be the best particular radar to detect a particular cloud at a particular height. But what you can see here is it is possible for beams from neighboring radars to overlap. And so what I'm going to be talking about is how we take the data from this polar coordinate system and we map it to a Cartesian grid, 3 dimensions. And then we think about how we put those on with multiple radar stations. And that's how we produce our sort of product that then goes into the spatial analysis. So hopefully that's like I don't know what that takes, 3 to 4 minute primer on ground-based radar. So this idea that the radar does its scan, and the fact that the scans can be done out of order now highlights this issue that, especially in a storm like a tropical cyclone, stuff's moving fast, it's changing fast. And so here we have data from Lake Charles radar during Hurricane Laura, and that was in 2020. That was a Cat 4, and it actually wiped out this particular radar. And so what I'm just showing here is when the scan was initiated, this is the first base scan, so they always start going straight out as possible, and then they tilt up. So here you can see, I just kind of showed these 2 features here of high reflectivity. So that means more signal coming back, basically. So that would mean higher rain rates inside these clouds. The greens would be really low rain rates. If you see any of the blues, that's probably not reaching the ground. And so these are areas that you would worry about in the red here. And then, so it scanned at that first elevation scan and then went up and did a whole bunch more, but it came back down and did the base again. So that happened about 3 minutes and 18 seconds later. Well, good. Well, I mean, how fast do these things move? So this is just sort of a quick estimation here, but I approximated it was about a speed of 30 meters per second. So if you know about like category 1 hurricane is 33 meters per second, that's 74 miles an hour. These things are moving fast. And this isn't even in the innermost rain band of the storm, where it would actually be moving around even faster. So just 3 minutes apart, you can see how fast they can move and also how much they can morph. So time offset, not only in neighboring ground-based radar scans, but also then trying to time it with a space overpass. This can be a very big issue. So this is the network of radars in the US. And don't worry about what the numbers mean. But you can see we've got really good coverage in the east. We've got a lot of overlap here. But the problem is when we've got overlap, each one of these at the National Weather Service office, or some of them are military radars, they're operated independently. So there's no synchronization. It's not like, oh, they all start the scan at the exact same time with the same pattern. No. They're all independent operators. So if you want to put them all together into Mosaic, you've got to work out a solution of the best way to do that. So you can do something like a very simple time distance weight with an easy interpolation scheme, which is what they do really quickly to make the national mosaic that you see. But they're usually not using the data from all the scans, so they'll just use that base scan. And they'll just forget the vertical of it, and they'll just pretend like it's flat, even though in reality, it sort of arcs. So the signal strength can vary, as I said before, the scanning timing. And then if you were trying to convert this to a rainfall rate, to do a rainfall climatology, the equation that you could use to do that could vary as well, depending on the season, the type of cloud. So it can be very complicated to blend data from multiple stations together. And so there's a big question about how do you treat the regions where there's overlapping data? Because it sounds good, oh, we got overlap, but then it also presents issues with how to deal with that. Okay, so let's go up in the sky. And let's go way up in the sky to the Global Precipitation Measurement Mission satellite. And so if you're familiar with the Tropical Rainfall Mapping Mission that was launched in December of '97, that provided us the first orbit that was synchronized around the tropics so that we could get a better sense of the diurnal variation in tropical rainfall. So instead of orbiting the poles, it was in a low synchronous sinuous orbit around the tropics. The GPM satellite has advanced on that. It can go a little bit further north to south now. So we are getting more data in the middle latitude. So that's kind of an advancement here with still really good coverage in the tropics. And they call it the GPM constellation because it really isn't just one satellite. Data are combined from multiple satellites. But this satellite itself has a dual frequency precipitation radar on board. And so I am not the expert in the DPR, but there are two different bands, different gigahertz, the KU and the KA band. And so as the arc sort of sweeps across, you end up with a swath that's about 245 kilometers wide. And the beam width is about 5 kilometers as you go. So, but it's on an irregular grid, right? Because the orbit is not like straight north, straight south. The Earth is spinning underneath as it's going over. So it's the data here are not just real friendly to map, and let's say ArcGIS. It doesn't like regular grids like that. So we've had a lot of challenges because I work in GIS and Kim works in not GIS. So, but she's the code writer. So we've developed our own common grid that we built. So this thing is vertical resolution then is 250 meters. And you have some advantages with this top-down view of the Earth because you're not going to have those weird density gradients. There's sort of a much more expected change in density over height. And you're not sort of cutting cross sections through storms. And so the signal return is a little bit more reliable when you're shooting straight up and down like this. So there are definitely advantages in the signal itself and in the processing of that. But this thing is moving overhead really, really fast at 7 kilometers per second. And so it takes about, you'll see some of the swaths of our tropical cyclones, but those overpasses are happening in maybe like 2 to 3 minutes. Whereas, remember, the radar scan, the ground-based radar scan might take 4 to 6 minutes. So trying to match those up, that can be a very tricky thing. But we do have data that are produced in the same units, decibels of C. So at least we don't have to worry about changing data units around. So just a brief recap of advantages and disadvantages, because each data set has advantages and disadvantages. So the 88Ds, they've been scanning, they started in 1995. The network was filled in by about 1998. And the data are freely available online, although there's 2.6 million points just in the 4 lowest scans per scan. So then forget all the other stuff on top of it, and every 6 minutes and 150 some stations, you get the idea, it's big data. So not just the average person will come along and work with this data, but they're publicly available. And you do get some overlap in the sites. So there's really good spatial coverage, especially over the eastern US. But there's so many limits with, especially with the beam spreading. We didn't even get into the blocking by mountains. Wind farms are disrupting the beams now. Sites going offline are being damaged by the storm, or the power goes out and they can't transmit the data. So then there's just long outage periods. And just the idea, again, that neighboring stations aren't synchronized. The DPR, that overhead point of view with the radar beam, is much more reliable. But the problem is then the overpasses are quite limited in their width, so you're not going to capture the whole storm in one overpass. You don't know if it's going to be in the storm center or not. It's a shorter archive. GPM was launched in 2014, so that's when our study period can begin. So we have fewer storms that we could look at. It's a little bit more coarse of a horizontal resolution of data set. So there's pluses and minuses to each that we've had to deal with in our research. So why study tropical cyclones? Well, they spend most of their life, they develop over the ocean. So that's out of range of our land-based detection network. And so we need to use these spaceborne sensors. But what we want to do is be able to figure out from the perspective of our long archive of data that we're getting with the ground-based sensors, are we seeing similar features at similar resolution if we do the spaceborne sensors? So are the rain bands being detected in a similar way or not? So there have been a couple of studies since GPM was launched, looking at some different types of weather systems and looking at different types of ground-based radars. The National Weather Service network is operating on a particular band, but in Europe they operate on different bands. So there can be different types of radars that they've looked at, different types of middle latitude weather systems. Winter storms are going to look very different on radar than a summertime convective thunderstorm. So the literature has said maybe about 3 to 5 DBZ bias with the DPR, the spaceborne satellite, being higher usually. But that kind of doesn't really get into the nitty gritty. But what we think about when we talk about like in weather forecasting, this idea of a bias is if the forecast model is over predicting by an amount that's relatively the same, we can correct for that bias. So this idea of bias in meteorology, you're always hearing about it. But it's never that simple in reality. And so that is what we got funding to do, is to try to figure out, well, how complex is this? How does it vary? What could be affecting it? And so there is some literature talking about that the type of precipitation could be an issue. That so we've got stratiform clouds that are your more horizontal layered clouds, and they would have smaller raindrops and lower rain rates. And then you have your convective clouds, your cumulonimbus, with the big raindrops. And a tropical cyclone has both. And so you've got your convective bands that wrap around, but then you've got stratiform areas on the edges of that. And then sometimes, especially after landfall, that convection dies down and you get a lot more of that stratiform precipitation. Or if you have frontal systems moving and that tropical moisture overruns it, almost like a warm front. And so actually you can get even more stratiform than convective precipitation in a tropical cyclone. So with those mixed precipitation types, that could be something that's affecting how each instrument is reporting back the reflectivity. So what we want to do is then look at the rain bands of as many tropical cyclones as we can get our hands on during the life of our grants, and do some comparisons between these two perspectives there. So I'll go over this a little bit quicker, since I just sort of explained basically how it comes in. But we limited our search for radars within 750 kilometers of the storm center. We tend to talk about this idea of being within 500 kilometers of the storm center. So we want to make sure we grab even radars that were just outside of that might be detected in there. And we created a mosaic, which I won't go into, but on a 1 kilometer by 1 kilometer horizontal grid. And then we did half a kilometer slices. And right now I'm just showing you the 3 kilometer slice because that has a nice continuous coverage and it's low enough that it's not in the melting layer, which artificially raises reflectivity values. We won't even go there. That's a whole nother lecture. So, and so then for DPR, we noted the time that the DPR overpassed the tropical cyclone center. And then we searched in our code to make a mosaic for all the radars that were near us that time. And so we're using version 7 now, which came out during the life of our grant. Version 6 had some issues with the sides not being as well adjusted on the side of the swath because the instrument kind of harps a little bit on the edge. And so again, we cropped the swath to within 750 kilometers from the storm center just to get started. There is a 14 DVZ minimum value that you can register on the DPR, which the WSR doesn't have that limitation. So that's something you have to keep in mind. But we ended up with 26 overpasses, and those had at least 1,000 matching grid points. So we have a pretty good about 69,000 points when we did the point-based analysis. But let me just show you 2 example storms that we've been working with and how different they can look. So here are the mosaics that we created with the ground-based radar. And these are the different radar sites. So you can see a storm like Isaias. Here's the circulation center of the tropical cyclone, but there was a frontal boundary. And so there was all this moisture overrunning. So you have precipitation extending way up into New York, even though the storm center is down here in North Carolina. So you had a lot of radars that you could mosaic together for that. And luckily, the trajectory of the overpass scanned a nice chunk of that. But you can see how narrow it is. So we don't get the full storm. So here's the storm center, but we get a nice area close to the center and we get some of this trailing stratiform as well. Versus here with Hurricane Laura was a Cat 4 when it made landfall. So we've got it just a couple hours before landfall. There's a nice, real well-defined eye wall that we were able to pick up. And we got just half of that here on the satellite overpass, but that's good. We really wanted to see that, as well as some of the rain bands on the outer side of that. But you can see the advantage of this, right? You can see the whole storm. Well, not the edge that's too far out over the water. You can see that line there. But so you have no control where this goes. You just, it's the luck of the draw. So how do we compare these? So Kim created what we call our common grid. That's a 5 kilometer grid. And so it basically covers this part of the country. And so we put all of our storms on to the same grid. And then we retained areas that were within 500 kilometers of the storm center. We call that our search radius. And so here you can see what that search radius is for Laura. Our ground-based radar mosaic that Town wrote the code for back when he was a PhD student here, puts it on that 1 kilometer grid, which, I mean, you can check, you can change that, and we tried a 5 kilometer, but it was very, very pixelated. Better to do a nearest neighbor interpolation to the 5 kilometer common grid. So we worked with that. We tried a couple different strategies. We tried a distance weighting, but the nearest neighbor seemed to be the most tried and true approach. We're getting as close to a 1-to-1 match as we possibly can. There were also masking data that would be outside of the radar network. And so these are only going to be areas that have values in both data sets, right? So here you can see the finished reflectivity for Laura. So Laura was a very compact storm, but we do have nice big high reflectivity levels over 50 DVZ that we were able to measure in Laura. So that was a good case study. So basically we're asking with the spatial analysis, how well matched are these reflectivity values from both of these perspectives? So we will have a point-based approach, which we are taking. And that's going to be basically Zainab's first paper out of her dissertation. She's been doing a lot of work in calculating the bias, the mean error, the absolute error. So I'm not going to present that. But I wanted to look for spatial clustering in the bias values. And so I ran optimized hotspot analysis for that. And I also did some correlation to try to explain maybe where some of this is coming from. Is it due to elevation, the distance to the storm center? We tend to have more convective clouds near the storm center and more stratiform away from the storm center. So that a little bit gets at that problem. The distance to the swath edge, just to check that there isn't a bias there, which that did check out, so we're good to go on that. And then the distance to nearest radar, is there an issue? Maybe it's because it's on the edge of the radar, the points are a little bit lower, and that's contributing to some of the low bias. We have an object-based approach then, which is what I've been developing for, I guess, 20 years now. And so instead of treating each point, which again, because especially the temporal offsets, the thing is gonna move. So if you got a point coming in and the data from this one, and then 3 minutes later, the data from this one, that rain band might have moved off. And so it's when it was detected, it might have been good, but now when you try to match it up because of an offset, you're gonna get a bias in there. You're gonna get a difference between the two values. And it's not that it's the instrument's fault, it's just a timing thing. And so the point base really penalizes that. Our idea with the object base is if you delineate the edge of the object, the edge could still have a little bit of issue, but the area in the middle is going to kind of move with the object. So it should help reduce some of that issue if you look at the objects that are of a particular reflectivity value. So with the object-based analysis, then when we're looking at reflectivity, 20 dBz is usually considered rain that would reach the ground, up to 40 dBz. We didn't have a whole lot of points that were higher than that. So our sample would be too small, the area would be too small to delineate. And so we calculated a number of spatial metrics, which I'll show you in a minute, but we'll just focus on a couple of them for this presentation. So, all right, what does this look like? Okay, so these are the points. Now, some of these are overlapped in GIS, so you're not seeing every single point that's underneath. There was over 69,000 if you combine the 26 cases together. But just so you can see them on the map, like where are all these points sampled? You can see kind of some of the overpass swaths, right, in there. This site had radars that went down, and so we are only having one radar where there should be 2 other radars. So we already know that that was going to cause a problem. So we're trying to figure out strategies around that. But basically, the blue areas is where the ground-based radar was higher, and the red and orange areas are where the spaceborne radar was higher. And so there does seem to be just visually, right, like out over the water, there's a lot more red. Then this radar sticks out with a lot of red, but then there's a lot more blue over this Gulf Coast area here inland. So there definitely looks like some spatial clustering is in there. So that's one of the reasons why I wanted to do the hotspot analysis. But before we get to that, just to give you some simple statistics. So when we subtract the two, we get a mean of about 0.5, about half of a decibel. So that's actually really good. It's a lot better than we were thinking, the standard deviation of 4.1. But when you plot it each storm individually, you can see there's a lot of variation here. So storm by storm, there's some different things happening because they're different sizes, different shapes, they're in different areas, different things are going on. The radars might be hot or cold, all kinds of different things could be going in here. So we ran some paired sample t-tests. So we're just, the hypothesis is basically the DPR and the WSR are the same. And so we're seeing if there's a difference there, if we reject that. So there were 2 TCs out of the 26, 2 cases where it did say they were similar. There were 5 cases where the ground-based radar actually had higher values, which goes against what the literature is saying that DPR should be so much higher. But then the other 19 cases, the DPR was higher. So I just boxed these out here just to kind of show you. These are the 5 that had a little bit below the 0 line, but most of them were above the 0 line, so DPR being high. But then there were also some outliers. This would be likely because the storm moved a little bit. And so you could go from having like high reflectivity to very little reflectivity in like the 3 minutes between, because there's offsets. So there is quite a range of values in there. So just to zoom in on our two cases here, Isaias and Laura, just to show a little bit more what these look like close up. So here is again the subtraction. So the red again is DPR higher. And when I ran the hotspot analysis, I color coded it so the hot spots would be red. So again, that's where DPR, the spaceborne, has higher values. And so you get a Z-score and a confidence interval. And so it'll plot, so the lightest is 90%, and then the darkest red is 99%. And then the cold spot would be where the WSR, the ground-based radar, is a little bit higher. And so in Laura over here, remember Laura's pretty compact. There's some small areas of spatial clustering, but not a whole lot. Laura overall was on the side of WSR being a little bit higher, which was interesting. But then Isaias, we see this distance from the storm center coming in here. So the storm center is here. And so the DPR seems to be detecting these stronger rain bands with even higher reflectivity than the ground-based radar. And I will tell you, I've done some digging into this, and station AKQ here in Wakefield, Virginia, its scan was 8 minutes late. So that was the closest time we could get. So it's very likely that the convection could have developed and moved a little bit, but that's something that I'm going to develop some techniques to go out from each radar and kind of zoom in and see if we're getting that clustering. Whereas out here, what we might be seeing is a bright band, because there was cold front and cold air overrunning here, and one of the radars that was detecting this area was actually going up through it, look like a melting layer. So that could be why we see higher WSR values here, that this radar scanning from above doesn't suffer from that same issue. So that's why Isaias is such a great case study for us versus the nice compact Cat4 Laura. So definitely saw some spatial clustering. We saw it in each of the different storms. I did run some correlation just to see how much explanatory value there could be in a couple of these different factors as a starting point. And so the distance to storm center came up as being something. They're all statistically significant because the N is so huge, right? But like, oh boy, 4%, woohoo! Don't write home about that one. But what's interesting is, so it is mostly the DPR actually is getting those higher values near the storm center. And again, that tends to be where there's more convection. So is the DPR either over or better, WSR is under detecting the higher reflectivity values. So perhaps we cannot assume a constant bias across the reflectivity values. So that is what that is suggesting to me. And we also see it then when we subtract the two. And then I also use the Z-score from the spatial clustering, and that increases the correlation coefficient even more. So there's something going on here with distance to storm center and how it's being detected. But it's not that the instruments are fundamentally different in every storm. So that definitely is something that we're going to keep looking at. Okay, so now onto my favorite, the object praise analysis. So with time limitations, we'll just focus in on 3 metrics here. So solidity, what we are doing is we are drawing a convex hull, which is the most simple polygon that can enclose your object. And then we are determining how filled it is. And so we've got the area of the simple one, and then we've got the area covered by your object. So the higher the value is, the more filled it is. So we scale it on a 0 to 1 because it's just basically it's a division problem. And so we've used that successfully on data from TRIM, the old GPM data, the TRIM data. So for TCs over the ocean, and found some good success with that metric in talking about storm intensity changes. Closure, that's one from my dissertation that got published in 2007. I called it the arc length back then, but we simplified it to closure. This is measuring the arc. So we're going tangentially around the circle. I developed this metric because I thought of a tropical cyclone as being the sort of spiral feature that closes and then opens. So how I've been using it previously is to measure that amount of closing or opening as the environment is affecting the storm. In this case, however, because of our limitations of the swath, direction, we may not get 100% closure. It may not be physically possible because the storm center is off the swath. But we can still use it to compare the two if we cropped them to the same area. So again, it may not be possible to have 100% closure, but what we basically do is take these pie shapes every 1 degree around, and basically if that pie shape has reflectivity in it for whichever value that we're looking at, let's say 40 degrees here, then that's considered a yes, and we add all those up, and that's the amount that is enclosed or close by. And then Stephanie developed dispersion for her dissertation, and that gives us a radial measure. So I've got the around, and then she's got the out. What we do there is we take the centroid of each polygon or each object, distance from the storm center, but we normalize it by the area of the object so that the bigger objects take more weight. And that gives us down to one location that would give us sort of a distance outwards. So that's kind of telling us how dispersed or compact it is. So we've got a radial, we've got a tangential, and then we got a how filled in is it. And just to kind of like give you the surprise now, this is the one that we're seeing a lot of difference in. Is how filled in is it? So just to show you what these metrics look like by reflectivity level in our 2 cases here. So the WSR is in solid, so that's the ground base, the space base is in the dash. And so how solid is it? So we can see that ECEs was a little bit less solid here, but then it gets more solid to the high reflectivity values, which is kind of interesting. And then how dispersed is it and how closed is it? And remember, we could never get to full closure with Laura because the center wasn't in the middle of the swamp. So we already knew we had that limitation. But the point is, these lines match really well for that. So you almost can't even tell the difference. So the instruments are detecting Laura radially and tangentially very well. Little bit of difference here. It's a little bit more filled in with the ground-based radar. With ECEs, we see more distance between these lines. It's not so bad at the lower reflectivity levels, but as we get to the higher reflectivity levels, there's more spread here. So there's something going on. There's a mismatch. And so we are trying, this is like hot off the presses, ways to visualize and do a sensitivity test with those mismatches. So if we subtract the metric value, like for the same level, 20 minus 20, 21 minus 21, 22 minus 22, that's the black line here. If they were detecting the same, that would run along 0. So that's the first reference point, is where is the black line? Is it above or below the line? So what we did was we said, okay, hold DPR constant, but subtract WSR. Subtract 1, subtract 2, subtract 3, subtract 4, subtract 5. All right, now hold WSR constant, subtract DPR, 1, 2, 3, 4, 5. So basically we're taking, if you're thinking about in a spreadsheet, right, we're shifting it up or shifting it down. So we're trying to get a sense of, is it match when it's 2 off or 3 off? So as a way of getting at bias with the spatial metrics. So we're trying this out and seeing if you have any feedback, that's great. Because we just started talking about this at our meeting on Tuesday. So the ones that are solid are the DPR was held constant, and then the ones that are dashed was the WSR was held constant. And so we go up to the higher value. So should be, if they're 5 dBz apart, they should be farther apart, right? So we should be spanning out from this line. And so for Laura, for solidity, so that's the one that there's a little bit more difference in the line. There's not a whole lot of difference, again, in the lower reflectivities. Once we get right in here to like 28 to 31 dBz, really it's the 2, so WSR being 2 higher. So again, remember in our point statistics, WSR was higher overall for Laura than DPR. And so we're seeing that mostly comes about in these reflectivity levels here. Not as much down for the lower and not as much for the higher, but really it's these reflectivity values in here. Switch over to ECEs, we get a little bit different story. There's a lot of spread, but it's symmetrical about 0. That's a good thing. The black line is pretty close to 0. We get about a 1 dBz bias that's towards the spaceborne radar side here, but then it's really mixed in these middle reflectivity values. And then what's weird is like the WSR drops below 0 and the DPR goes above 0, which is not how we set up the map. We thought this is how we would fit. So, but we are seeing some interesting things with basically E to the E and the higher reflectivity values, just like we saw in the spatial clustering, are much higher. And the WSR are much lower at those high values. Whereas they match much better in the middle to low values. So again, there's a difference depending on if it's maybe the stratiform versus the convective clouds that are being sampled in how the spatial arrangement is. If we look at closure, so closure, again, for Laura, there was a lot more agreement, and we can see that here. The black line is right along 0, maybe a little bit of a +1 here for WSR being a little bit higher, but overall fairly symmetrical about 0. So whereas East to East, it starts out okay, but then once we get above about 30 dBz, now we're closer to the 0 line is this orange one, which is DPR being about 2 dBz higher. So we are seeing that it's a little bit, so the arc, the 360 arc, is being represented differently in the two. So you can see that, I mean, we never get 100% closed in either one of these, but these match pretty well here. Whereas for East to East, when we get to the higher reflectivities, you see how there's like more pieces and there's more spread out and there's more space in between. And so because of this little guy right here, closure is a lot bigger down here. With that little guy being gone, then this becomes the outer edge and this is the outer edge. So we're seeing some differences. And so we have to back this one up by 2 dBz. So to match this 35, we have to go to 33 on this one. I don't have space, I can show you all of them. But that's basically what this is telling us there for closure. And then for dispersion, again, Laura turned out well. It was a compact storm. It wasn't spread out, so there wasn't actually a lot of space to be taken up. ECS was a very spread out storm, just in its geometry overall. And then you can see what a difference it can make because the biggest piece carries the weight. This piece is all conjoined. So it's centroid, let's just say it's right about here, but these are all spread out, and so they're adding more weight to it. So the centroid's probably further out on this one. So we have to go down to lower reflectivities to get these to fill in and come back together to match this shape. So that's what this is telling us. So closure-wise, it can really depend on what's going on right around the eye. But solidity-wise, you can see it makes a big difference if, again, we got our simple polygon. It's going to be a much different amount of fill because this is connected and these are all separate. So all these little gaps are going to add it to being less solid. So it really is a connectivity thing is what we're thinking about in terms of how these areas are being represented. Okay, so I will go ahead and wrap us up here. I could keep going, but I'm sure you don't want me to. So overall, in general, the DPR values are higher than the WSR values. So that does back up what we saw in the literature for other weather systems. However, we did not see a consistent bias across storms or across these different metrics that we looked at it, and we looked at it different ways. So you would not want to just say, oh, we will take and add 2, and then that will correct the bias. No, definitely not. Don't do that. It varies amongst each TC, but we also think there's issues with the different radars and even within the TC, how the convection is being detected. But all TCs did have a statistically significant spatial clustering. So you only saw 2, and Laura had the least actually. So this particular storm here has a lot. And so again, this idea that the inner core of the storm, closer to the storm center, where there would be more convection, tends to be higher in the spaceborne radar. The outer region tends to be higher with the ground-based radar. Our metrics, solidity varied a lot more than closure, and the WSR was way too dispersed for ESA-ES. Even when we went 5 dBz apart, they were still way too different. Because all those lines were below the 0 line, which is not what we expected. So we're going to keep exploring that a little bit more. So one of the things we want to do is check the radar timing. I had done that in-depth look for ESA-ES and found that 8-minute offset. Unfortunately, when we run our mosaic, we don't have a report easily generated that would tell us which time was full. It saves it, and I can go in each folder and write it down. But we're thinking about checking for that and pulling those radars out and see if that helps with some of this. And also just checking, let's say, 100 kilometers around each radar and seeing within the different radars, potentially, there might be one that typically runs full, and that's why the values are going to be a little bit lower for that radar. And then again, stratiform versus convective regions. So Zainab's doing this where she's looking at the point-based analysis, but she's looking at bias within the different reflectivity levels. So it's not just one number for the whole 20 to 40, but we've got it in 5 dBz chunks that are moving across, and we're actually plotting that change in the bias. So this figure is a good one, I think, that shows there's a potential issue with the radars. One, this is where the ground-based radar is higher for Mobile, Alabama, and then this would probably be Slidell. So either this one's running colder or this one's running hotter, but it's the same spaceborne satellite going overhead, right? So so looking for spatial patterns like this and coming up with ways to look at that. We do have to be careful because we're not saying that the NWS is somehow the radars are bad. It's just a function of how they operate. But we need to know that to better apply our knowledge that's based on this to what we're getting from the spaceborne, so that when we're looking out over the ocean at the spaceborne data, we know that we're picking up similar regions of convective clouds in tropical cyclone systems. So, thank you.
For your presentation, I think we all like our research, but you are as passionate as you are. But I had a question. You spoke a bit about the limitations of radar. So what options are there? Do you think like LiDAR could be used in this kind of setting? Would that be better? Or are there other technologies that would be, if we don't consider the cost of saying LiDAR?
Well, yeah, I mean, because the problem is you would need like a network that's always like on, like gaming, like I can't even imagine what that would cost. I mean, they are working to upgrade the ground-based radars. I mean, they have been for a lot of times with this idea of a phased array system to try to deal with some of the limitations of the way they have to scan and scanning strategies. But we've invested obviously like billions of dollars in the network that we have. And it's been upgraded throughout the years and things like this. So it is much higher resolution now. So yeah, I'm not sure people are really keen on developing another kind of network on it, but yeah, I mean, it would be more like, I mean, a calibration issue. I mean, they run some checks on it, but it costs a lot of money to run like the big check that they would need, where they would take like the spherical ball and hang it out and get a known signal back and be able to adjust the power output. Like, I'm trying to think, like, how did they do that? They have a big crane that goes out there and hangs the thing in the, because these things are way up off the ground, right? They're not just sitting on the ground. So it's like, very time consuming to try to calibrate the network. But that's one thing that, if the calibration was improved maybe a little bit, that could help a little bit. But yeah.
So my student's going to laugh at this one, but in terms of where you're trying to go with this, obviously you're trying to work out strengths and weaknesses of the two different systems. Obviously I have the bias with Spaceborne, but are you ultimately going to be able to do some kind of data fusion with the products to get the strengths of both and somehow integrate, acknowledging some of these biases, but then putting them both together and getting a more complete understanding, or is that not where you're going?
That's not where our group is going, because we want to do more like tropical cyclone rain band detection in and of itself. But I believe that is where, NASA and NWS would want to go in the future. And so that could be partially why we got funding to try to start looking into this. So that's really just the first part of the grant, is just this sort of overland check. The other phases of the grant were over water.
looking at moisture regimes and looking at like storm evolution under different environmental conditions, and then looking for those overpasses to look at the rain bands and look at the actual vertical structure, which we haven't gotten to vertical structure. So we spent 3 years on this. Just trying to figure out how to grid these things together. I mean, there are studies that instead of mosaicing the ground-based radar, they actually just kind of take the points in space and match them up. So like in, I guess, 4D space. But for the object-based analysis, we need a flat plane. And so that's one of the things that I'm trying to come in and say that helps forgive a little bit of this temporal offset. If you have the point cloud, I mean, you can match the points, but you're not going to see the features. So you won't really know where the edge of the rain band is. You really can't measure the rain band in the point cloud way. So I'm trying to come up with like, no, this is a valid thing. And we can do it with these objects, with these like flat sheets, and then we can kind of build up from that. So I'm trying to sneak that one in there. Sadie.
So kind of playing off a little bit of your answer to the first question, given the price of, the cost of trying to do micro adjustments on a giant array or putting in a brand new array, when you do find a finding like this radar is running hot or this radar is running cold, do you feed that back to them? And then my question after that is, if they then responded to you recommending that, would that change the ability to apply a sort of one-size-fits-all bias correction? Because I know this comes up a lot with like ground truthing stations when they go a bit wonky and then somebody fixes them. And then it's like, well, in this part of this year, you can't apply that bias correction. It's like, how on earth do you program that into something automatic, right? Like, where does that go in the code?
Yeah, I mean, Stephen Mullins might have a little bit better of a sense just because he's worked with operational folks. My understanding is they're a little sensitive about these kinds of things. Especially since it's like so far in the past, it's kind of like, well, that was 10 years ago that you're working with that storm. What do you want us to do now? Kind of thing. So I don't know if there's just funding for them to do like a real-time, real intensive, like maybe even by region or something, like where they get a bunch of neighbors together and then they calibrate and they go after it and all of that. There just may not be the money and the time and the personnel and all of that. You will see sometimes like NWS jacks, the radar will go down for a couple of days because a part broke and they're waiting for it to be ordered and a tech to come and install it. And it is what it is. So sometimes the hurricane's coming and shoot the radar, they need maintenance on it and it doesn't detect the storm. Like, So yeah, I'm sure there are budget considerations in that. But that is something that we've been trying to think about when we're thinking about publication is we don't want to be like pointing fingers and just saying, well, your network's not so good. Like, well, it is what it is, but what can we still do with it? And I am not a signal processor. I am not a radar. I've never had a class in radar. So everything I've learned is by reading articles and going to conferences and all that. So I would, the person, to say a word about it, it would have to be somebody who's, sort of a physics kind of guru that understands signal processing.
Will a radar always run hot, always run cold? So you always get this sort of pattern regardless of the storm that's coming through that you're analyzing. So for this location, will it always be this really clear red blue split that you get?
So I don't know let's say like in a calendar year, how often they may try to perform. So there is like a quick calibration they try to run just to keep the signal that's going out consistent within a certain DBZ, like noise level. Yeah. So that is sort of an internal check that they do. So they're not like going whoa, 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 all over the place. But just in terms of then over time, that signal can kind of migrate. So internally it's still consistent, but relative to everything else, it sort of migrates. I don't know if there is like a schedule that they do that on or how frequently they do that. But that's, I've just heard by going to conferences, people say like such and such a radar tends to run hot. But some of it is just like how the thing is installed, how recently was the thing that turns it, like checked and tight, bolts tight, whatever it is, like, it's not easy mechanics in there to have this thing like whirling around constantly, so. It could be like, oh, they just replaced it, they just did maintenance on, now it's great because it's running smoothly and the signal is consistent and they've tested it. But then if it doesn't have a problem for 3 years, maybe it doesn't get the big calibration, I don't know.
I hate to keep this like at this table asking questions, but it's all about us. You opened your talk saying that precipitation can really morph and right and just what it looks like in general. And so I'm wondering for your object-based analysis, I guess, especially when thinking about these maybe timing issues with the actual radar, the differences in time, and then the storm speed itself and how the patterns might change. Are there any limitations to kind of the object-based analysis and how well you can match those patterns based on storm speed?
We have, so one of Town's papers was using this idea of a Lagrangian trajectory with like a spiral arc to it. And he just did a test on sort of one storm and then like graduated up. But the idea is that if we did it, that idea on different storms, can you adjust somehow in the code, right, by storm speed and sort of like, it's part of it's the vorticity of the storm as well, how tight the spiral is going to be, plus other, things that are getting in the way, like vertical wind shear and all this other stuff. So it's not like a nice, pretty, perfect spiral shape. But we do use in our code, in our Mosaic code, we do use the Doppler velocities. So you can get, that's the advantage of the Doppler radar. That was the 1988. That's where that comes from. 88D is Doppler. 1980 is when they started developing that Doppler technology. So that basically we can now see motion of it. We can get a motion vector off of it. And so his code does calculate those motion vectors and then use that when you grid the data onto the grid. So you can get a little bit of like real time, like now, like motion to it. Okay. Although it's not a 360 motion, it's basically towards or away from the radar. So that's another problem is the radar scanning. If the weather system is coming like right towards it or right away from it, or if it's at a right angle, if it's at a right angle, you can't get those speeds because you only got inbound and outbound. That's because that's the direction the signals is traveling. So you can get a little bit of motion just off of like the real time, and then you could try to sort of project that. But again, with everything, like you could try to have some sort of, and that's why I would wonder like how much of a standard you could apply to that or how much variation you could try to get a better fit. And then how variable is that? Because the problem is it might be a little bit smoother when it's out over the ocean before it's out of radar range. But once you get over land, you have so much like the friction, the differential friction of the land surface, whether you're going over a forest or a city or you're over the beach, and you're just getting so much change that's happened really quickly. It's not just the wind advection anymore. But that's kind of complex too.
Not a question, but a quick comment. So Berry got stuck on YouTube only. So she can't ask questions, but she has a whole bunch for you. She's gonna follow up afterwards with you, and she just wanted me to let you know. She's like, can you put me on the phone? Well, I'm excited right now.
So we're out of time. I'm sure Dr. Matcha is happy to speak with you after the class if you have more questions. But enjoy the rest of your day, and let's give another hand for Rupert.